And for two electron functions and operators, so if you have to have for each S operator, you have to have it for electron 1 and electron 2. So an S squared operator, a 2 electron S squared operator is then S electron 1 plus S electron 2 plus, so that is S plus here. That's the sum of the two plus operators for both electrons. And then you have times S electron 1 minus plus electron 2 minus. And I took the plus combination, so let's plus, minus, minus, yeah. So I have to have a minus now. Then I get a set for 2 electrons, and that is S1 set plus S2 set. And then finally S set squared plus S1 set plus S2 set squared. So that's my 2 electron S squared operator. Now what are 2 electron spin functions? I mean, the 1 electron spin functions are alpha, beta, and so forth, alpha and beta. And for the 2 electrons, I guess we have, in principle, 4 possibilities. We can have alpha for electron 1 and alpha for electron 2. We could have alpha for electron 1, beta for electron 2, beta for electron 1, alpha for electron 2, or beta for 1 and beta for 2. And if I think of permutation of the electrons, this and that are symmetric. But the ones in the middle, they are neither symmetric nor antisymmetric. If I permute the 2 electrons, I go from this to that and vice versa. So they don't have permutation symmetry. Let's have a look at the 2 middle ones with respect to whether they are eigenfunction of S squared. Because of course we would like to have spin functions which are eigenfunction of S squared really. So they correspond really to a proper spin state. So let's apply this S squared to alpha beta. And I don't write the electron 1, electron 2, otherwise we'll never get finished. On alpha beta. So the first one is always electron 1 and the second one is electron 2. Right, so I have to apply all that here to that. So let's take them one by one. We'll do it first. Well, I hope you don't mind if I do some instant mathematics. Reuse that. So I have S squared on alpha beta, which means I have to have alpha beta here minus alpha beta there, alpha beta here. So let's apply this parenthesis first. So I just copy the first one, S plus S2 plus, okay, S1 minus on this one. I mean, this is a linear operator, so I let first this one act on that, and get one term, and then I let this one act on that and get one term. And this is S1, so that's only going to act on the function which goes with electron 1. So this is going to act on alpha. S1 minus on alpha gives us, that gives us beta, right? And this operator is not doing anything with the function which goes with electron 2, so that stays as it is. Plus, what is S2 doing? S2 on the alpha is doing nothing, because that's the electron 1 function. But S2 on beta, S2 minus, S minus on beta gives us 0. So here we have 0. Minus S1 set on alpha gives alpha back. That's a half, and I get the same function back, and then nothing is going to act on this one, so I get alpha beta. Now we let S2 set act on this, so I definitely get alpha back for the electron 1, because that's not doing anything. But S2 set on beta, that gives us minus 1/2 beta, which means that the whole parenthesis is 0. Now, that one is actually just this one squared. So I could sort of, if I wanted to, write it up, let it act once, let it act, sort of write it as product of two parentheses, let the first parenthesis act, but that I know is already 0. That was actually quite fast. So the only thing I'm left is this part here. So now I have to let this one act on beta. Now what does that? S1 plus on beta gives us alpha, but it doesn't do anything with the spin function of the second electron, so that's alpha beta. S2 plus doesn't do anything with the electron 1 function, so that stays beta, but it increases the second one, gives alpha. So what do I get back? I let S squared act on alpha beta, and I don't get alpha beta back. I get alpha beta plus beta alpha. So this function is clearly not an eigenfunction of S squared. So I can't say what the spin of this function is, because it's not an eigenfunction. I can say what the MS value, what the capital MS value is. Let's do that for a second. But actually that we did here, that was this. That's S set. So that is actually 0 alpha beta, alpha beta. So that's 0 times alpha beta, which means that the capital MS value is 0. But I can't write an S value up, or an S squared value up here, because that's not the same function. Now I could, and I guess, I hope you're going to believe me, I could do now the opposite. That was sort of a little parenthesis. I could look at S squared beta alpha. And that, I could do the same story again. But whether it's alpha beta here or beta alpha makes no difference for the result at the end. I just get the minus sign for the first operator and the plus for the second, so that goes out. That's 0, that's still 0. And here, sort of, I end up first with alpha alpha, and then I get the same. So that also gives me alpha beta, or probably it gives me beta alpha plus alpha beta. So again, I get the same. So what I could try instead of, I could try, so neither this is an eigenfunction, so those two are not eigenfunctions of S squared, but I could try to let S squared act on 1 over square root 2 alpha beta plus beta alpha then. Well, I know what it does on alpha beta. So the 1 over square root 2, I mean, that's not affected by S squared, so I take that before. And then I let the S squared act on the first one. That gives me alpha beta plus beta alpha. Then I let S squared act on the second one. That gives me alpha beta plus beta alpha, which means I get 2 divided by square root 2 alpha beta plus beta alpha, which actually is 2 times 1 over square root 2. I know that's a bit silly, but this is my original function. So I get my original function back. Woo, it's an eigenfunction. Multiplied by 2. Now we know that spin eigen, that if it's an eigenfunction to S, then the eigenvalue is S times S plus 1 times the original function. That's sort of, well, let's write here. That's what it's supposed to be. So what's the value of S then? Patrick? That's going to be 1. For if S is 1, I get 2 here. Because we know that the eigenfunctions to S squared always have this as the eigenvalue. So this function is actually a function which has an S value of being 1. And the MS value, I mean, if the MS value for each part is 0, that's still 0. Yes?
Why the 1 over square root of 2 wouldn't it work if you didn't have that as well?
Yeah, I mean, it would work. Yeah, sure, it works for the S squared. That's just a normalization.
Oh, sure. Okay.
But right, yes. Good. So this is the MS0 component of the S equals 1. What is this? Because that's an MS1, and that's an MS minus 1. So those are the other 2 components of the S equals to 1. So this one plus, because this is MS1 of S1, and this is MS minus 1 of S1, so they are the 3 components or 3 orientations for the S equal 1. So those are the triplet wave function. But if you can do a plus combination, we can also do a minus combination. S squared alpha beta minus beta alpha. But that's going to give us 0. So this is the S equals to 0, and then therefore, of course, MS equals to 0 wave function. So that's the singlet spin, 2-electron spin wave function. And this one, together with those 2, are the 3 triplet wave functions.